Hello everybody and welcome to chapter 8.2 of Advanced Functions. Today we're going to be continuing with dealing with different types of combined functions. Specifically today, we're going to be dealing with the product and the quotient of two functions. So first we're going to figure out how to actually work with those. And then we're going to talk about different applications of these functions as well as things we could do with them and must understand. So let's get started on that. So let's first talk about the product of two functions. The product of two functions can be easily found and it's going to be as easy as you think. It's simply the multiplication of two functions. I know, it's incredible. However, the most important thing you have to understand for every type of combined function is that the domain of these functions has to be common to the component functions. So for example, if we had a function f of x such that f of x has to be greater or equal to or x has to be greater or equal to 0, and then we had another function that was defined for every number out there, the domain of the combined function would take the common domain. So it would be such that x is greater or equal to 0. So for example, let's do one right now. If we were asked to find what h of x is equals to, if h of x is equals to the product of these two functions, and these two functions are equal to these two equations, we would simply just multiply the two, right? So we could write out what h of x is equals to, plug in the two equations, open the brackets. So we again just distributive property, multiply that by x squared, multiply this by 48x, and then we get this line over here. Collecting like terms, we get this equation. So this equation, as you can see, is a polynomial equation of order 5. We haven't really dealt a lot with these, but you should still remember how you would tackle such a function. Again, you will have to know everything from the course to do well in this chapter. It is super important for you to go and review chapter 1, chapter 2, chapter 3, chapter 4, and chapter 5, and chapter 6, and chapter 7 to understand what's happening here, because you need to know the core of all these functions. If you don't know how to graph a sinusoidal function, you will not know how to graph a sinusoidal function multiplied by an exponential function. So back to this question here, it's a polynomial. So how do we graph a polynomial function? Well, we need to find its zeros. How do we find its zeros? Well, we learned the factor theorem, right? To factor any type of polynomial function. So now you're gonna go back to chapter 2.3 if you don't remember it and look at how you do that, which is why this chapter is super complicated. However, if you are on top of your game and you remember everything, you should have no problems. This chapter takes so long in terms of just pure knowledge components that you will not be dealing with anything too complicated. Because again, if you're dealing with such big numbers and such various, a lot of different equations, your teachers cannot possibly expect you to also perform super complex calculations on top of that. You simply will not have the time nor the mental capability to balance that many factors in your head. So overall, when we're talking about the product of functions, just multiplication. Multiply function A by function B. You found out function C. Now identify how you can graph it. When it comes to working with quotients of functions, it's extremely similar. Guess what? Instead of multiplying now, you're dividing a function by another function. So again, dealing with its domain, it's super important for you to understand that not only must the domain be common to both of the component functions, it has to be also further restricted to exclude any values that make the denominator equal to 0. Again, this is division. If we have a 0 in the denominator, we have a mathematical error. Your calculator has no idea what is happening. You don't know what is happening. Nobody knows what you do when you're dividing by 0. So you have to now account for restrictions. Again, if you're dealing with that, just simply state them right before you start doing any calculations, and that should be more than enough. Again, let's look at an example. So here, it's asking us to analyze the function h of x if h of x is equals to f of x divided by g of x, and f of x and g of x are equals to these functions here. So again, I just substituted them in, and we got over here. You could probably try to simplify this. You could probably try to like take the log of one side and log of the other, so you could get an exponential function instead. But the most important thing for us to do right now is actually talk about the domain. If we don't check the domain exists in the first place, we could face a lot of trouble. For example, if our function didn't have a domain and we tried to solve for it, we would be wasting our time. Because if it's not solvable, you don't even need to try. So let's look at the two components we had. The first component was f of x, and f of x is equal to the square root of x minus 9. This is a radical function that you learned in grade 11, and it is super simple. We know we can't take the square root of a negative number. So when does the values within the brackets or within the square root become negative? When x is less than 9, right? If x is 8, 8 minus 9 is negative 1, we can't take the square root of negative 1, and so it is not defined. For that reason, the domain of f of x is that x has to be greater or equal to 9. Looking at the domain of g of x, we've been learning about this. Again, the logarithmic functions, they have a regular asymptote at x is equals to 0. So now we have negative x minus 3, that minus 3, and that negative x, we can factor it into negative x plus 3, and that x plus 3 cannot equal to 0, right? So then solving for x, we find out that x cannot equal to negative 3. However, we can't go below negative 3 either. We can't have the logarithm of negative 1, right? For these kind of problems once we're actually solving it. And so the domain of g of x is that x has to be less than negative 3. So now when we want to graph h of x, we know it has to have the common domain between these values. So we have x is greater or equal to 9 and x is less than 3. As you can see, these functions do not overlap anywhere, right? And so now we just figured out that h of x actually has no domain. If it has no domain, it is not a function. It is not something that we can graph. It is not something we can work with because it simply does not exist. So if you're facing something like that, we can write it as the following. So sorry, this should be a division. Come on, no. Yeah, so this should be a division symbol. Divide. There you go. We would write this. This means the domain. So this, you could write this as a fancy like cursive D for the domain. But either way, the domain of f of x, or f over g of x, is equals to the 0 with a line through it. What this means is an empty set. There's no domain. You might encounter this before, for example in 8.1, if you are adding again something that don't have an overlapping domain. So this is the notation you would use to express that. Lastly, if we did have a function that had an overlapping domain, so for example, if instead of being x is less than negative 3, it was x is greater than negative 3, we would have a common domain of x is greater or equal to 9. For that, Once we identified what the domain is, we can now talk about how to actually graph these functions. Again, for this, I would actually like to move for the next slide so we could actually talk about it more in depth. But if you had two of the same types of functions, for example, a polynomial divided by a polynomial, that would be a rational function, and you know how to do that. But if it's two different types, I will discuss how to do them now. So the most important and the most difficult part of combining functions is the pure understanding of what they mean and how to apply them and their properties to the real world. For example, I got this beautiful function from the textbook. It was talking about a scientific thing you can perform to decay something, and this is the function that it is defined by. As you could see, we have something with sign and also a power. We haven't seen anything like this before, and quite clearly we shouldn't know how to graph it. But nobody's stopping us from splitting this function into two different parts. We know that what the two different parts are. We know what this is, right? This is our sinusoidal functions. We learned how to do them in chapter 4 and 5. And this is a exponential. Actually, this is not even exponential, is it? This is just a single term. I know it is an exponential. Sorry, I'm just confusing the two. It's an exponential function. We also know how to graph an exponential function from chapter 6 and 7. So what we could do to graph the overall large function is actually graph function 1 and function 2. If we do them on the same set of axes, we can actually see the common domain that they have, right? For example, we know that the sinusoidal function is defined for every value of t. An exponential function is also defined for every value of t, just the range is different. So, if we were to graph these two functions, we can now actually use the superposition principle to make the new graph. You might be confused on why that is, and that's understandable, but remember, multiplication is simply just repetitive addition. So 3 times 5 is 3 added by itself 5 times. So 3 plus 3 plus 3 plus 3 plus 3 is equal to 3 times 5. So using that kind of knowledge, nobody is stopping us from applying this principle onto multiplication, because simply we're just going to be adding those values a repeated amount of times, which shouldn't interfere with our points or key points. So actually, let's take a look at that. Okay, so here I put the graph into Desmos. Again, you won't have this kind of resource on an actual test in school, but I want to show you this so that me and you can derive it together. So this is what the function looks like. As you can see, you can probably tell the little bit of a sinusoidal characteristics of these like ups and downs, crescent and valleys. So for actually graphing this function, I had to change the t values to x because Desmos is picky, and I set a value to the 3 other components. Again, if I were to change them, you see that the whole graph changes, and if I were to change these, they also change. So there you go. Let's make them whole numbers for happy time. There you go. So now let's analyze the 2 parts that we talked about. This is part 1. We know how to graph this. This is a sinusoidal, so stretch factor of 2, horizontal compression by factor 1/6, and we have to move the graph. Actually, the c value is not even part of it. So there you go. That's the only 2 things we have to talk about. So there you go. Pi/3 is our period. If we were talking about the second part of the function, again, exponential. We know that this is always going to be a key point. Then we could identify another one. For example, if we were to substitute 1 into it, we would have 0.5 to the power of 1 times 1, we could find something. Where's 0.5? 0.5. Come on. It's very difficult to get it exact, but yeah, this should be 0.5. Or rather, there you go. So yeah, again, we know how to graph this kind of function. And as you can see, the range is that it has to be greater than 0. Combining the two might seem a little bit complicated, but to be honest, it's not. So for example, let's analyze what happens at 0. What would be the two functions that we're multiplying? The purple one and the green one. The purple one, when x is equals to 0, is equals to 0, and the green one, when x is equals to 0, is equals to 1. So if we were to do 0 times 1, we get a 0. So now our main function should have something at 0. Is that true? That is true. Now let's look at another point. Let's look at point 1. So again, on Desmos, you could just make a straight line that can help you identify the 2 points. So at 1, again, we had a 0.5 for the green one, and for the purple one, we have negative 0.558. Okay, so if we were to multiply those two numbers together, we get negative 27.94. Is that what we get on the red one? As you can see, that is exactly what we get. So you could go and select the points you like on both of these graphs and simply just multiply them together. So if we were to measure what x at 3 makes these two graphs equal to, we have 0.125 and negative 1.502. Multiply those numbers together and we should get negative 0.1877. So yeah, using that, we can actually graph it. And a better way to do this, quite personally, instead of choosing whole numbers like we have here, we can actually start dealing with the key points of a sinusoidal graph, right? So here, we discovered that the period was pi over 3, if I'm not wrong. Yeah, so then a quarter way through would be pi over 12. So choose pi over 12 as your key point number 1. So we'd have substitute pi over 12 into this, pi over 12 into this, and solve, and you would get your first maximum, or local maximum. And then you could do the same thing for the valley, and then you would get your local minimum. Again, these values are much more important. Also, since we do have zeros of a sinusoidal function, we know that our main function should also have zeros there, which is, again, exactly true. So yeah, as you can see, the principle still works. So now instead of adding the two coordinates, we can actually multiply the two coordinates and it still works. Another thing that we must then discover is what happens when we divide two functions, right? We still have no idea, for example, how to divide. Again, let's just use the same kind of question. There it is. As you can see, it is not as pretty, I would say. It now seems to be reflected to this side. But how would we deal with this? Well, nothing is still stopping us from using our two sub functions. Again, now we select a key point, for example, again, pi over 12, substitute it into here, and evaluate. So if we were to divide 2 by, let's see, x is equals to pi divided by 12, 0.6 divided by 0.83, let's see how much that equals. 2 divided by 0.834. That is 2.4 around. If this is around 2.4, we should be good. Is this around 2.4? It's around 2.4. So as you can see, it is pretty close. As you can see, like these 2 points are a little bit different, again, because of this this graph over here. But you will never be asked to sketch the perfect graph. because quite frankly, it is really difficult on a chart paper or a graph that you make yourself. And so your teacher might be asking you to sketch the graph, but it will not be like replicate the perfect graph of this function. So don't worry about those little differences here. As you can see, like how much is it differ by? It's really not that much. 0.26, 0.8, 2/100ths of a difference. Like your teacher will not notice that. But if you understand how to do it, you should have no problem graphing any type of functions whatsoever. So now if we were talking about a logarithmic function divided by, again, a sinusoidal function, you could just graph the two together, identify key points, divide the two key points by one another, and then create your new graph. Overall, hopefully that made sense, because now I'd like to actually talk about the homework. So the homework for today is 6 questions, however, I think 3 of them are word problems. The word problems are not complicated, however, they will be testing whether or not you understand how to multiply and divide 2 functions together, how you could identify a common domain, how you can actually analyze what those values mean. So for example, if you are talking about, let's see, question 11 is talking about how a trend is defined by this type of function, you need to, for example, talk about how you would obtain a clear representation of what the graph means. So again, we're talking about populations and economic plans. So you'd clearly be talking about the relationship between the two and how the population or how much money, for example, be given per person per a period of time. For other questions, we also are dealing with even or odd or neither functions. So if you don't remember how to do that, that was part of like chapter 1, if I'm not wrong, where you found that f of x is equals to f of negative x, then it is even. If f of negative x is equals to negative f of x, the function is odd, and if it's neither of those, then it's neither. So again, a lot of this chapter, it's pure testing whether or not you remember things from the past. And for that reason, I'd really recommend you make sure you understand everything from chapters like 1 to chapter 7 thoroughly before jumping into chapter 8, just because if you don't understand them, it will make your life really difficult. You don't want to be making mistakes within those basic functions, because if you make a mistake in a basic function, your more complex function will have such a big margin of error that I'm not sure your teachers would accept it. But yeah, hopefully I didn't scare you away with that comment. Again, if you have any questions, feel free to leave a comment down below. I'll be more than happy to try and help. I think we only have 3 more lessons to do. I'll have to check whether or not chapter 8.5 is like, again, making connections, or if it's an actual chapter we should cover. So I will let you know by the end of chapter 8.4. But yeah, hopefully you have enjoyed today's lesson. I've really had a lot of fun teaching you guys, and I can't wait to see you next time. Bye bye!